All right, physics students. Continuing on with Chapter 11 here. Archimedes' principle. Well, if you look over here at this picture, and we just have this imaginary chunk of water in this imaginary surface. The weight of this water has to be held up, so the pressure is higher at the bottom than at the top, as we discussed. And the difference in those two forces, upward and downward, is equal to the weight of the fluid in there. So if I were to fill this up with some other substance other than water, the weight would be different, but the net force upward would still be the weight of the water because it's determined by the pressures of the rest of this fluid. That means that whatever object I put in here is going to be pushed up with what we call a buoyant force, and that buoyant force is equal to the weight of the fluid that it displaces. This is a fairly reasonable proposition, and it was arrived at by a guy named Archimedes about 2,500 years ago, before any of this other stuff was around. So the buoyant force on an object that's submerged in a fluid is equal to the weight of the fluid that it displaces. Okay, so example, a swimming pool, raft. Yeah, well, if an object is floating, then the buoyant force is equal to the magnitude of its weight. That's just the upward force, which is buoyancy, and the downward force, which is weight or balancing if it's floating in equilibrium. So, if I replace this chunk here with a substance that has less density than water, it's going to have a buoyancy force that's bigger than the weight, and it's going to pop up to the surface. If I replace it with a substance that's more dense than water, for instance, then it would sink because the buoyancy force would be less than the weight. So that's what determines whether an object floats or sinks. If it has a density greater than water, it sinks. If it has density less than water, it floats. If it has density equal to water, it just sits there, suspended. Okay, so assuming a raft is made up of solid square pine wood. Whether the raft floats in water, determine whether the raft floats in water. Well, I know what it does because I've thrown a piece of wood in a bucket of water before and it floats. Determine whether the raft, and if so, how much of the raft is beneath the surface. Okay, take a look at this picture. Give me a picture. This doesn't look like a raft. Determine how much of the raft is beneath us. We're missing a picture for this or something. It's not anywhere near enough information. Yeah. I don't see that. Looks like these notes are missing something here. I'll try to do a homework problem that's similar to that example. Let's finish up the chapter first here before I go digging around for the rest of that problem. Okay, fluids that are flowing. Steady flow, the velocity of fluid particles are constant, so it's a steady flow. Unsteady flow means that the velocity at a point is changing. Makes sense. Fluid flow can be compressible or incompressible. Most liquids are pretty incompressible with normal pressures. They don't change their density. Compressible or incompressible refers to whether the density is changing. If they get compressed, their density goes up. If they get incompressed, if there was such a word, their density goes down. Fluid flow can be viscous or non-viscous. Viscosity is the frictional forces that fluids exert on one another. And then an incompressible, non-viscous fluid is called an ideal fluid. Okay, so we're going to restrict our discussions for fluid in motion. We're going to restrict our discussions to a steady flow and an ideal fluid. So we're going to assume that there isn't any friction among the different layers of fluid, and that the fluid's incompressible. That is, we don't apply pressures that compress the fluid. This is mostly applies to liquids. Gases are very compressible, so they don't behave like an ideal fluid. Okay, the equation of continuity. If you have a steady flow through a pipe that looks like this, the amount of material coming into the pipe every second at this end has to be the same as the amount of material going out of the pipe every second in this end. And that's called a continuity equation. That the mass is not created or destroyed in here, and it's not compressed. So if you look at the volume of this cylinder going in, the amount that it travels in is in a certain amount of time is the velocity of the fluid times the time. And the volume of the fluid that flows in is this cross-sectional area here times this width, or length in this case. So, and the density times the volume is equal to the mass. So, plugging all that stuff in, the amount of mass per second that's flowing into this tube is given by the density times the velocity times the area. And the density that's flowing out, by the same reasoning, is given by the density flowing out and the area, the cross-sectional area here, and times the velocity here. So the velocity is going to be, since the area is smaller here, if we assume these masses are the same, or densities are the same, if the this makes sense. If the area is bigger, the velocity is smaller. So the fluid's moving slower down here than it is up here. We've all put our thumb over a garden hose, shrunk the area, and got a higher velocity of water flowing out. Well, the equation of continuity says these two things have to be equal, but if it's in an incompressible fluid, then these densities are the same and they cancel. And the area times the velocity at every point along the flow, the area times the velocity has to be the same. And that's the equation that we'll use. Okay, well, here is a garden hose example. A garden hose has an unobstructed opening with a cross-sectional area of that. It fills a bucket with a volume of that in 30 seconds. Find the speed of the water that leaves the hose through the unobstructed opening. And an opening with find the speed. Well, the speed, I know for part B, the speed is going to be twice as much in part B as it is in part A, so I can take care of that. In part A, I'm going to need a formula. I think it fills a bucket in 30 seconds. Find the speed of the water. Okay, so I'm going to use the equation they had in the delta M over delta T is equal to the density of the liquid, which is water, times the area times the velocity. And this is what I'm looking for. Notice I'm using a little v for velocity. We have volumes and velocity here. Okay, what is the mass of a bucket with a volume of that in 30 seconds? The mass, delta M, that I get in 30 seconds is going to be the density of water times the volume of water. Notice I'm using a capital V. They give me the volume of water, so I'm going to put the density of water here times the volume of water, which they give me. And they give me time, which is 30 seconds. And I'm going to have a rho on this side of the equation, so they're going to cancel. They give me the area, and they ask me to find the velocity. So I think I can do this. The rho's will cancel. The volume that I get is 8 times 10 to the minus 3 cubic meters. Everything's in good units here. And the time I get is 30 seconds. And the area, they tell me, is 2.85 times 10 to the minus 4th meters squared. And the velocity is what I'm looking for. Okay, well, to find the velocity here, I just have to divide both sides by 2.85 times 10 to the minus 4th. I think you folks can work through that. Okay, so if it's got half the much area, the answer to part B is going to be twice as much as part A. So that's not too bad. Okay, this is going to be the last topic in the chapter, I think, Bernoulli's equation. Bernoulli's equation is the work-energy theorem applied to fluids. It's derived in your book. I'm not going to derive it here. I'm just going to look at it, and I think we can see where all these terms are coming from. The pressure here on both sides is what's doing the work on the fluid. Pressure exerts a force on the fluid over a distance, and so it does work. The 1/2 rho V1 squared and the 1/2 rho V2 squared, I think, look kind of familiar to you. They come from the change in kinetic energy of the fluid. This is the conservation of energy, by the way, or the work energy theorem, I guess, for a fluid, since pressure is doing work. And rho Gy1 and rho Gy2 are the come from the potential energy of the fluid. So when the pressure, when a difference in pressure does work on a fluid, it can change the kinetic energy and change the potential energy. And if there's no viscosity, which is friction, using up the work done by the pressure, then the kinetic energy of the fluid and the potential energy of the fluid have to be what changes when the pressure does work. Okay, well, I'm just looking at this equation a little bit. Like I said, I don't want to drive it, I just want to look at it. Suppose y1 and y2 are the same. In that case, we wouldn't have, these two terms would go away. And then this would say that the pressure plus 1/2 rho times the velocity squared is a constant. That means if the velocity is high, the pressure is low. High velocity, low pressure. Okay, that's definitely, that's called the Bernoulli effect. And here's an example of it in action. When the truck is sitting still here, this tarp is just lays flat. But when it starts moving, the velocity of the air above the tarp is bigger than the velocity of the air below the tarp, which is inside the truck. So this is going to have low pressure when it starts moving. Low pressure. That means that the pressure underneath the tarp is going to be bigger than the pressure above the tarp, and so the tarp will puff up like that. That's Bernoulli's principle in action. An airplane wing is another example of Bernoulli's equation in action. An airplane wing is shaped like this. The velocity of the air above the wing, because this air has to travel a bigger distance in the same amount of time as the air flowing underneath, the velocity above the wing is greater than the velocity below. And so the Bernoulli, there's a lot of aerodynamic effects on a wing, by the way. Airplanes are a little bit more complicated than this. But this is one effect that helps keep airplanes in the air. The velocity is higher above the wing, so the pressure is lower above the wing. Pressure is higher below the wing, and that pushes the wing up, that force. This is totally wrong. I left it in here because I just wanted to point out to you that the Bernoulli effect causes a spinning ball. If the ball is spinning like this, which it is for a curved ball, Bernoulli says that the ball would go this way. It's not the Bernoulli effect at all. It's called the Magnus force, I believe, that causes a curved ball to spin. So this is one of the bigger errors I've seen in any physics book in some time, I must say. I'll have to look in the book and see what they say, but that is totally wrong. It's a nice story, but it turns out to be wrong. Okay. So, this is a little application to Bernoulli's equation. The pressure, this is an emptying tank, common situation. This is going to be Y1 up here, and this is going to be P1 up here, and this is down here is going to be Y2 and P2. Okay, the fluid up here is moving with this is going to be V1 up here, the velocity of the fluid up here, and this is going to be V2 down here. That's called the efflux speed, the speed with which the fluid's coming out of this tank. And so, applying Bernoulli's principle, P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. Okay. Number one, the pressure up here is the pressure of the atmosphere, 1 atmosphere. And the pressure down here, where the water's coming out, is P2, the pressure of the atmosphere. So P1 and P2 are the same. I can subtract them from both sides of this equation. We assume that the velocity of the fluid up here at the top, where you've got this great big surface, we're going to assume that the velocity up there is 0. The fluid's hardly moving at the top of the surface. It's really moving down here. So V1 is 0. And Y1 minus Y2 is equal to H. So if I bring this to the other side of the equation, I get rho G y1 minus y2 equals 1/2 rho v2 squared. The rows cancel. I can bring the 2 over. y1 minus y2 is h. And I got a squared, so v2 is the square root of 2gh. Not too amazingly, that's exactly the same thing you would get for the velocity if I took an object here and I just dropped it from rest down to here. Its velocity would be the square root of 2gh. You know, that's not too amazing that you get the same result for a fluid that's moving down without friction or drag, because this is assumed to be an ideal fluid. It's not too amazing that the velocity of the fluid is just like it had fallen from the surface of the tank, because it comes from the same equations, the energy conservation. So that's the efflux speed formula, and I don't see anything else. I don't see any examples or anything. So I'm going to go find a couple of examples, homework problems to work for this, to add a little bit to these notes. These notes are sort of lacking in examples, I think. So that's it for our last section. Will be in this chapter will be